Welcome back to Educator.com. Today we're going to talk about the idea of a function. Functions are extremely important to mathematics. You've certainly encountered them before, but you might not have fully understood how they work and what they're doing. This lesson is here to give us a clear understanding of what it means for something to be a function and how functions work. Since functions are so important, they're going to come up in every single concept you learn about in this course, and they're going to come up in every single concept you talk about in calculus, and they're going to keep coming up as long as you're studying math. Make sure you watch this entire lesson. It's so important to have a good, grounded, fundamental concept of what a function is, because it's going to keep getting used in everything that we talk about. This is probably the single most important lesson of this entire course, because so many later ideas are going to talk about functions. Also, it would help to have watched the previous lesson on sets, elements, and numbers, because we're going to be talking about how sets are connected to functions. So if you don't have that under your belt, I'd recommend go watch that one first, because it'll help explain a lot of what we're talking about here, as functions are relying on the idea of sets. All right, let's jump into it. What is a function? A function is a relation between two sets, a first set and a second set. For each element from the first set, the function assigns precisely one element in the second set. So we'll point at some element in the first set, and it will say, here's an element from the second set. We'll point at another element from the first set, and it will tell us, here's some element from the second set. That's the idea of a function. Here's a visual example for it. So we could have something where all of the squares are the first kind. It's our first set. And all of the round things on this side are our second set. So second would be the second column, and first set would be the first column. So we could have news gets put onto paper, right? We say news, the function gives us paper. We say cheese, the function gives us burger. We say good, the function gives us buy. We say sand, the function gives us paper. We say bubble, the function gives us gum. So there's only 5 elements in our first set, only 4 elements in our second set, but this is a perfectly reasonable function. News, paper, cheese, burger, good, buy, sand, paper, bubble, gum. The only one you might be wondering about is, well, wait, news goes to paper and sand goes to paper. There's no problem with that. We only said that the function has to give us something when we point at something in the first one. We never said that it has to be a different thing for every single thing that we point to. It just has to give us something for it. So that's what we've got here. We've got something where everything that we call out on the first side, we call out news, and in turn it responds by telling us paper. We call out good, and in return it says buy. That's how it's working here with this function. Here's a non-example. So this one, we say tree, but the function gives us 4 different possibilities. Sometimes it spits out maple, but other times it spits out oak, but other times it spits out apple, but other times it spits out pine. And then fruit, if we go to fruit, it sometimes spits out apple, and sometimes it spits out grape. This isn't allowed because it's only allowed to give one response to a given input, right? We tell it one element from our first set. It can only tell us one element from the second set. It's not allowed to give us a whole bunch of different choices to pick and choose from. Sometimes it's going to be maple, sometimes it's going to be oak, sometimes it's going to be pine. No, it has to be one thing and one thing only. That's what it requires to be a function. So this is not an example. This is not allowed, because we can't have it be multiple things coming out of this. It has to only be one input, will only give us one output. And as long as we keep putting in that same input, it can only give us the same output. Just like variables, it's useful to name functions with a symbol. So let's talk about how notation works here. Most often the symbol we'll use to talk about a function is f, but sometimes we're also going to use g, h, or whatever else will make sense depending on the context. But often we're going to wind up seeing f. If we want to talk about what f assigns to some input x, if x is the element in our first set, if that's what we call the element in our first set that we use f on, then it will be assigned to f of x. F acting on x, what f spits out when given x. So the first symbol is the name of the function that we're using. Then the second symbol is the second symbol in parentheses is what the function is acting on. So f, the name of our function, acting on x, and then that whole thing together is f of x. F of x is the name of what comes out of it. So f is the name of what's doing the acting. X, if the whatever's in the parentheses, The first symbol is the name of whatever is doing the acting. The thing inside of the parentheses is the name of what is being acted on. And then the whole thing taken together is where we are when we use the function on that element, what we get output to, where we come to. Now, there could be a little bit of confusion that f of x, because it's f parentheses x. And we know that parentheses, if I wrote like 2 in parentheses and then 3, that would mean 2 times 3, right? So we might think f times x, but we're going to know from context that f is a function and not something that we multiply. So when f is a function, we don't have to worry about using multiplication if it's f on some element. So it's always going to be f of that element, never f times, unless we're talking about that explicitly. But if it's just in parentheses, it's not going to be multiplication. So when you see parentheses and it's a function, it isn't implying multiplication like when we're dealing with numbers. If we want to express what sets the function acts on, we can write f colon a arrow b. So what this is f goes from a to b. It takes elements from A, our first set, and then it assigns them elements from B. Normally, it won't be necessary for us in this course, and probably for the next couple of years, it won't be necessary to name the sets that our function is working on. But why that is, we'll discuss later. It's going to be pretty simple, but we'll discuss it later when we get to it. There's a lot of metaphors that we can use to help us understand what's going on in a function. Here's 3 metaphors to help us understand what happens when f takes things from A and goes to B. So our first idea is transformation. The function transforms elements from one set into another. It takes an element x contained in A, takes an element x in A, and then it transforms it into an element in B, which we call f of x, or f acting on x. F of x is what it has been transformed into. That's what it is after the transformation. Now, from problem to problem, the rules for transformation will usually change as we use different functions. One function is generally going to have a different set of rules for how its function works than another function. But if we're using the same function, if we're in the same problem using the same function, the rules never change. If we put in the same x, we will always get the same f of x as our result. The rules for how the transformation always is the same. So if the same thing goes in, the same thing always comes out. Another way we can look at it is a map. It tells us how to get from one set to another set. It is sort of a guide, a way, directions. It is directions for how to get from one place to another place. Of course, if we start at a different starting location, a different starting place, different elements in A, we might end up at a different destination, different elements in B, right? If I say go 100 kilometers north, you're going to end up in totally different places if you start in Mexico, if you start in California, if you start in England, if you start in South Africa, if you start in Japan. Each one of these places, if you start in Egypt, each one of these places is going to wind up going to a totally different place, even though they're all still the same direction. You're still doing the same thing. You're still going 100 kilometers north in all of these cases, but because you started at a different place, you end up at a different place. So a different starting place, a different element that we're acting on, a different element that we're mapping, will normally cause us to have a different destination, a different place that we land on. The map itself, though, never changes. If we start at the same place, we always arrive at the same destination. So if we start in San Jose, California, and then we go 100 kilometers to the north, I actually have no idea where that is, but we will be 100 kilometers north of San Jose. And then if we start in San Jose again on another day, and then we go 100 kilometers north, we're going to wind up being the exact same place. And if we go to San Jose, and then we go 100 kilometers north again, we're going to wind up being in the exact same place. And people are probably going to wonder, why does this person keep showing up here? But it's because we're following the same map. The directions, the transformation that the map gives us, the way we go, isn't going to change each time. It only changes when we start from a new place. Finally, one last way to visualize it is the idea of a machine. We can visualize a function as a machine that eats elements from A and it produces elements from B. What it produces depends on what it eats, but the machine is reliable. If it eats the same thing, it always produces the same output. So for example, if we've got X, right? We've got X right here, and we shove it into our machine, F. It goes into the machine, then the machine works on it, crunches it, crunches it, crunches it, and it spits out F of X. So we're going from the set A to the set B. Now, one thing about the machine is that it's perfectly reliable, right? The machine is reliable. If it eats the same thing, it produces the same output. If we put in x, it will always spit out f of x. So the first time we put in x, it spits out f of x. The second time, f of x. The third time, f of x. The 50th time, f of x. Just like when we started in San Jose and we went 100 kilometers north, each time we always wound up coming to the same place. You put the same thing into the machine, the same thing comes out. This idea is so important, we're going to talk about it really explicitly. We've said this one way or another for all of our different ways of thinking about functions. But it's so important, it's such an important characteristic of a function, we want to make sure that we know it. If we put the same input into a function, it will always produce the same output. Now, the input and the output could be totally different. The input isn't necessarily going to be where we show up in the output, right? You start in San Jose and then you show up in some farmer's field 100 kilometers to the north. But you're going to come out to that same farmer's field each time because you're showing up at the same location. So for a function to make sense and be well defined, for it to work, its rules must never change. So for example, if f of 2, if f acting on 2 spits out 7, if f of 2 equals 7 the first time, then f of 2 equals 7 the second time, and f of 2 equals 7 every time. So no matter how many times f operates on 2, no matter what, it's always going to spit out the same thing. That's what it means to be a function. Your rules don't change when you are going on the same thing. You work on everything, you work on one element the same way each time. You always map it, you always transform it, you always assign it to the same place. Here is something that is not a function. G of cat equals fur. G of cat equals whiskers. G of cat equals quiet. This can't be a function because we've got three totally different destinations when we plug in cat. And what determines whether we go to fur, whiskers, or quiet? There's no reason why we should use one set of rules or another set of rules, so it's not a function. There's no reliability here. We don't know when we plug in cat if we're going to go to fur, whiskers, or quiet, so it's not a function. But we could have a function that was h of fur goes to cat. H of whiskers goes to cat. H of quiet goes to cat. It's not that there's a problem with having us land on the same place, right? No matter what we put in, the function could spit out cat. It doesn't matter as long as it's not having the first thing, the first set we're coming from can't split as it comes out. We can land on the same place, but we can't be coming from one place and go to two different locations. We always have to follow one rule, and because we're following one rule, we can't land on two different things. Let's look at a non-numerical example. Before we start talking about how functions work on numbers, let's consider an example of one that works on something totally not about numbers. Let's think about a function that gives initials. So we'll define f is going from names spelled with the Roman alphabet. So, names like Vincent or John, not things that are spelled with characters that we can't express in the Roman alphabet. And it's going to go to letters from the Roman alphabet. So f of x equals the first letter of x. F of x is going to be the first letter of x. Now, if we go, wait, we know x, the first letter of x is x. Yeah, but what we're talking about is names. X is a placeholder. Remember, when we talked about variables, the idea of a variable is that it's a placeholder. So x is just sort of keeping the spot warm until later we slot in a name. So if we decide to put in Vincent into the function, then this x on the left side tells us where to put Vincent on the right side. So Vincent will slot in here on the right side as well. We'll have Vincent go on the left and Vincent go on the right. F of Vincent would be V, right? We hack it off just to the first letter. F of Nicole would spit out N. F of Padma would spit out P. F of Victor would spit out V. F of Takashi would spit out T. Whatever we put in will spit out just that single letter, right? So if we were to turn this into a diagram, we could have Vincent here, Nicole next to Vincent, Padma, Victor, and then finally Takashi. And so this is where we're coming from. And then we're going to letters, right? So we've got V and N and P and T. And let's put in another letter like, say, S and Q. So Vincent gets mapped to V. Nicole, by this function, gets mapped to N. Padma gets mapped to P. Victor also gets mapped to V. Takashi gets mapped to T. But does S and Q get used? Not for this set of names. Maybe if we put in Susan or we put in Shucks, there's got to be a name with Q that I don't know offhand. Let's pretend that the name is simply Queen. I'm sure there is a name Corey, a really weird spelling of the name Corey. There is a name out there that is spelled with a Q. I just don't know it offhand. So there is something out there that can fill out that S, that can fill out that Q. We just don't have it in what we're looking at so far. So there might be other things that we aren't hitting on the right, but everything that we've got on the left is what's getting mapped to stuff on the right. So the functions we use, of course, it's no surprise. This is math. We're probably going to be talking about numbers. So it shouldn't come as a surprise. We're going to concentrate on using these functions with numbers. So functions, as we just saw, can be used for lots of things, but we will focus on functions and the real numbers. Unless we're told otherwise, we will assume every function takes in real numbers and outputs real numbers. That is to say, f is taking in reals and then spitting out reals. Okay. So when we are given a function, we'll usually be told what its rule is, how it maps inputs to outputs. So for example, if f of x equals x squared plus 3, its rule is square the input. Since x is our input, then what we do is we first square the input, and then we add 3. So square the input and then add 3. That's its rule. That's how it works. Notice that x acts as a placeholder. Just like it did with the names, it acts as a placeholder. It's not that x is really the thing we're worried about being acted on. It's just telling us what's going to happen to whatever we plug into this function. If we plug in 3, what will happen to 3? If we plug in 50, what will happen to 50? If we plug in smiley face, what will happen to smiley face? No, x is just there to sort of keep a spot warm. It's telling us, here's the place, things will go into this place. And things will go into this place wherever I show up on the right side as well. If we want to use a function, if we want to evaluate a function at a specific value, we just apply this rule to whatever our input value is. In practice, this turns out to actually be really simple. Usually we're given a formula for each function, so we just follow the method of substitution. Remember, we take whatever we're substituting in, we wrap it in parentheses, and then we see what we get. So if for example our function is f of x equals x squared plus 3, then to find f of 7, we just plug in. So 7 is what we're plugging in. So we have 7 in this spot, and a 7 will go in here. So we wrap that in parentheses just in case. In this case, we don't have to, but we'll see why it's useful to always remember to wrap in parentheses. So 7 squared plus 3, 7 squared is 49. 49 plus 3, we get 52. If we want to look at a slightly more complex example, though, we see why it's so important to wrap your substitutions in parentheses. So if we consider a slightly more complex input like a plus 7, then we have to have it in parentheses because it's not just the a that gets squared. It's not just the 7 that gets squared. It's all of that thing that went in. All of that thing is both the a and the plus 7. It's a plus 7. That's that whole number combined. It's not a squared plus 7. It's not a plus 7 squared. It's a plus 7, whole thing squared, and then plus 3. A good way to see the behavior of a function is by creating a table of values. Sometimes we call it a t-table because it has the shape of a t, right? On one side, we have input values, while the other side shows us what the function outputs when given that input. So normally, the left side will be our input value, and the right side will be our output value. So for example, if f of x equals x squared plus 3, then we can spit out a bunch of values for it. So if we want to figure out what happens to f of negative 2, we just follow the normal thing. F of negative 2, so we plug it in, negative 2 squared plus 3, so we get 4 plus 3, we get 7, and that 7 shows up here. If we want to figure out what f of negative 1 is, we do the exact same thing. Negative 1 squared plus 3, 1 plus 3, and 4. And that 4 shows up here, and so on and so forth. We just plug in, based on this rule, whatever the rule we've been given, we plug in whatever our input is, whatever the thing on the left is, any of these numbers. And then, once we figure out what this number is here, we evaluate, and we get what its corresponding value is on the right side, and we write that in, and that's how we make a table of values. Having this table is often a very useful way to quickly analyze and see what's happening in a function over a large range of possible inputs. Domain. The domain is the set of all inputs that the function can accept. So the domain is what can go into the function. It's the inputs that we're allowed to use. It's what our machine can eat without breaking down. While we generally assume that all of R can be used as inputs, all of the real numbers can be used as inputs, sometimes certain values will break our function. The output won't be able to be defined. Thus, our domain is normally going to be all of the real numbers except those numbers that break our function. Occasionally, we might actually get things where we're going to be given a explicit domain, like just evaluate it from -3 to 3 and forget everything beyond those -3 and 3 values. But normally, we're going to assume all of R except for those things that break our function. Let's see an example. If we had f of x equals 1 over x, the function would be defined as long as we don't divide by 0, right? If we have x equals 0, though, if we had x equals 0, then f of 0 gets us 1 over 0. Are we allowed to do that? No, very bad. We cannot divide by 0. So we're not defined there, so everything else works, though. If we plug in anything that isn't a 0, works out fine. So everything is defined as long as x is not 0. So our domain is all numbers except 0. So the domain of f, to show all numbers except 0, it's everything from -infinity up to 0, not including the 0, and then union with everything from 0, not including the 0, to infinity. So that's just another way of expressing all of the real numbers with the exception of 0. Now, for now, we mostly only have to watch out for dividing by 0 and taking square roots of negative numbers as the only two things we have to worry about breaking functions. Remember, you can't take the square root of a negative number because what could you square that would still have a negative with it? Any number squared comes positive, so we can't have a square root of a negative number because it'd be impossible to give me a number that you could square into making it negative, at least as far as the real numbers are concerned. Later on, we'll talk about the complex, but that's for later. So right now, we only really have to worry about dividing by 0 and taking square roots of negative numbers. Those are the things to watch for. That's where our domain will break down. Later in the course, we'll have a little bit more to worry about. We'll also have to worry about inverse trigonometric functions. Those are only defined over certain things, and also logarithms. They have some parts that they're not allowed to take either. But right now, just dividing by 0, taking square roots of negative numbers, and later on, much later in the course, after we see these ideas, we'll have to think about them as well when we're thinking about the idea of what can go into a function. Domain is what goes in. Range is what comes out. Range is the set of all possible outputs a function can assign given some domain. So with some domain to start off with, these values are what's able to come out. The range is what can come out given some domain. These values will always be in the real numbers, unless we're dealing with a set that isn't working in the reals. But they don't necessarily cover all of the reals. For example, that function we were working with before, f of x equals x squared plus 3. The lowest value that f can output is 3, right? Because the smallest number we can make with x squared, well, x squared always has to be greater than or equal to 0, because there's no number that we can plug into x and square that will cause it to become negative. The lowest we can get that down to is a 0, so the lowest we can make this whole thing is when this is a 0 plus 3, so the lowest possible output is 3. We can produce any value above 3 with x squared, though, so we can just keep going up and up. So our range would be everything from 3, including 3, up until infinity. So it's all of the reals from 3, including 3, and higher. Great. If we want to look at an example that doesn't use numbers, we could talk about that initial function, that function that ate names and spit out first initials from earlier in this lesson. In that case, if the domain is all names, then the range is all 26 letters of the Roman alphabet. Even though I still can't think of any names that start with a Q. Queen, let's say Queen counts. Okay, Queen Latifah, right? It's got to count. So then we can have that be the range, 26 letters of the Roman alphabet. So we plug in, because if we're looking at all the names that could possibly exist, well, there's Albert, there is Bill, there's Charles, there's Doug, there's Elizabeth, there's and so on and so on and so forth. So there's always something that will spit that out. But if we restricted the domain to the 5 names that we saw earlier, Vincent, Nicole, Padma, Victor, and Takashi, then we only had 4 letters show up. We just had N, P, T, and V show up. So in that case, if we restricted our domain to a smaller thing, our range would also shrink. So the range depends on what our domain is. If we're looking at what our normally, we look at everything that can go into the function, and that's normally how we think of the domain. So the range is everything that could come out. But sometimes we'll be given a more restricted domain, and we have to think in terms of that more restricted domain. All right, ready for some examples. First, nice easy ones to get us warmed up to this idea of plugging in. If f of x equals 3x minus 7, what is f of 2? So we just plug in. If we use red for this, f of 2, we plug in 3, plug in that 2, minus 7. 3 times 2 equals 6. 6 minus 7, so we get negative 1. Let's use blue for this one. If we have f of negative 4, then 3, we plug in that negative 4, minus 7. 3 times negative 4, negative 12, minus 7, we get negative 19. Oh no, what if we have to use something that is a variable? No problem. We still just follow the exact same rules. F of a, well, what happened to x? It became 3x minus 7, so now it's going to become 3a minus 7. So we get 3a minus 7. And what if we want to do b plus 8? Same thing, f of b plus 8 equals 3 times b plus 8 minus 7. So we have to distribute, and notice how important it was that we put it in parentheses. If we just plugged it in as 3b plus 8, that'd be totally different than 3 times the quantity b plus 8. And that's what it really has to be, because it's everything in here that got plugged in, not just the b. The b and the 8 don't get to be separated now. They have to go in together. So 3 times quantity b plus 8 minus 7, we get 3b plus 24 minus 7, which is equal to 3b plus 17. Great. Next one, what if we wanted to fill in a table? G of z equals z squared minus 2z plus 3. If we had to fill in this table, then we could do negative 1. So g of negative 1, negative 1 squared minus 2 times negative 1 plus 3 equals 1. Negative 1 times negative 1, 1. Minus 2 times negative 1, so plus 2 plus 3 equals 6. So we get 6 here. Next, g of 0, 0 squared minus 2 times 0 plus 3. Well, that simplifies to just 3 because those zeros, they disappear. If we want to plug in g of 1, then we get 1 squared minus 2 times 1 plus 3. So 1 minus 2 plus 3 comes out to 2. We plug in g of 2. We get 2 squared minus 2 times 2 plus 3 equals 4 minus 4 plus 3, which is 3. We plug in 10. We get 10 squared minus 2 times 10 plus 3. 10 squared, 100, minus 2 times 10, 20, plus 3 equals 83. And there we go. So you just plug into the function exactly as you would to set up this table. You're told what your input is, and then over on the right is your output, based on the rules of the function. So the function gives us some rules, and so we plug in inputs like negative 1, and negative 1 goes through negative 1 squared minus 2 times negative 1 plus 3. We get 6, and that's what's going on when we're making a table of values. If h of x equals 2x squared plus bx plus 3, and we know that h of 3 equals 15, what is b? So in this case, we're looking to figure out what b is, right? Now, we know what h of 3 equals 15. We know that h of 3 equals 15, so we need to somehow use this to figure out b. So we go, oh, hey, I could plug in 3 and I would get something different than just 15, right? So h of 3, based on the rule, is 2 times 3 squared. So we're switching for where all the x's show up, right? X here, and that's it. So 2 times 3 squared plus b times 3 plus 3. So we get 2 times 9 plus 3b plus 3, which is 18 plus 3b plus 3, or 3b plus 21. Now, at this point, we go, right, I also know that h of 3 equals 15. Well, this is still h of 3, right? So now we go h of 3 equals 15, and we swap it out, and we get 15 must equal what we know h of 3 is. We know that h of 3 is equal to 3b plus 21, and we also know that h of 3 is equal to 15. So since h of 3 is two different things, but it's still just h of 3, we know that they must be the same thing. Otherwise, there's no logic there, right? So 15 equals 3b plus 21. We subtract 21 from both sides. We get negative 6 equals 3b. We divide by 3 on both sides. And we get negative 2 equals b. Sweet. Next one. What's the domain and range of f of x equals 12 minus square root of x plus 3? What's the domain and range of this? Now remember, domain is what can go in. Range is what can come out. So what we first want to do is we first want to figure out, do the domain first. What can go in without breaking this function? So is there anything that can break in this function? We go, oh, right, square root breaks when negative inside, right? We can't take the square root of -1 because there's no number that you can give me, at least no real number that you can give me, that would square to give us -1, right? You give me any positive number, comes out positive. You give me a negative number, comes out positive. You give me 0, comes out 0. So there's no number you can give me that will spit out a negative number when squared. So square root breaks when we are trying to put a negative inside of it. So when will this break? Square root of x plus 3 breaks when we have a negative inside. So when is x plus 3 going to be negative? When x is less than 3. Sorry, not less than 3, but less than -3. So if x is less than -3, if x is more negative than -3, then this will be a negative value inside. We'll have x, if for example we use -4, then we'll get the square root of -1. If we put in -50 billion, then we'll get square root of -50 billion plus 3, which definitely still be negative. So it only stops being a negative inside when we actually get to -3. So -3 is an allowed value because square root of -3 plus 3 would be square root of 0. We do know what the square root of 0 is. It's 0. So the domain works for 3 and higher, right? Everything is still reasonable higher than that. So our domain is going to include 3, and it's going to go anything higher than that. So that is our domain. If we want to figure out what the range is, then the question is, what can f of x put out? So notice we've got 12 minus stuff. Now that stuff, square root of x plus 3, square root can spit out any number, right? If you put in square root of 0, square root of 1, square root of 4, square root of 9, you're going 0, 1, 2, 3, and you can make any number in between that. So 12 minus stuff. So what's the smallest that stuff could be, right? The smallest number that stuff could be is 0, right? So stuff is smallest when square root of 0 equals 0. So the biggest number we can get is 12. 12 is the highest number we can get, the largest number we can get out of this function. What's the smallest number we can get? Well, you can just keep giving me larger and larger x to make our square root a bigger and bigger negative number on the whole, right? So it'll be minus larger and larger numbers, so 12 minus larger and larger numbers, so we can keep going down. So any number below 12 can be achieved, because we can just keep having the square root pump out slightly larger numbers, which since we're subtracting by these larger and larger numbers, will keep going down. So any number below 12 can be achieved. So we have our range is going to be everything from the lowest possible all the way anywhere up from -infinity up until 12. Now we ask ourselves, can we actually achieve 12? Yeah, we can. We can actually get to 12, so we include 12. So our range is from -infinity to 12. There's our answer. Final one, we've got a word problem. Give the area of a square, A, as a function of the square's perimeter, P. And then also say, what is the domain of the area as a function of perimeter? So first, as we talked about in the word problems, let's set up what our variables are. Nicely, this problem already gave us our variables, but we'll just remind ourselves. A is the area of square, and P is the perimeter of square. So we also probably wouldn't hurt to draw a picture so we could see what's going on a little more easily, right? So we've got a square here. So here's our square, and we're talking about the area of it and the perimeter of it. So that's everything that we don't know offhand. We don't know the area, we don't know the perimeter. They're going to be somehow connected because we somehow want to be able to make a function out of area where we plug in a perimeter and it spits out an area. We basically want an equation that has area on the left and then stuff involving perimeter. We're solving for area in terms of perimeter. That's another way of looking at what this function is going to be. So we need some way to be able to connect these two ideas. How can we connect the area of a square to its perimeter? Well, maybe we don't see a way right off the bat, but let's just think, well, how do you find the area of a square? Well, it's its side times its side, right? It's its side squared. So the area of a square, now we might as well go back and we'll set up a new variable, right? We didn't have that before, so side of square. So side of square is a way to get our area. So area equals side squared. Now we still want some way to connect the area to the perimeter. So what we want is, well, we might not be able to connect them directly, but we've got area connected to sides. Maybe we can connect perimeter to side. Oh, right, yeah. And if you've forgotten what a perimeter is, what do? You just go and look it up, right? You've got access to all sorts of information at your fingertips. It's so easy. If you look up perimeter, you're like, oh, I've heard this before, I can't remember what it is. Type it into an internet search. Next thing you know, you'll have a definition for what perimeter is. So perimeter is all of the sides put together, all the sides added together. So we've got 4 sides. So perimeter is equal to side plus side plus side plus side. All of the sides of our square, or 4s. So now we've got a way of being able to have area talk to perimeter. So area equals side squared. Perimeter equals 4 times side. So perimeter over 4 equals side. Now we can take this and we can plug it in here. So area equals, since we're plugging in, we're substituting, we do it with parentheses, squared. Area equals perimeter squared over 16. We have to square the top and the bottom. And there we are. We can think of area equals perimeter squared over 16 as a function because it only depends on what we plug in for perimeter, right? Area will vary as we put in different things. So we can think of it as a function acting on perimeter. We plug in a number from perimeter and it spits out what the area has to be. So we can just rewrite this as area is a function of perimeter where it's equal to the perimeter squared over 16. It's just a different way of thinking about it. We can think of it as an equation, or we can think of it as a function where it just works the exact same way that the equation worked, right? There's no functional difference between area of perimeter equals perimeter squared over 16. The area based on a function using our perimeter equals perimeter squared over 16 compared to area equals perimeter squared over 16. They have the same effect. It's just 2 slightly different ways of talking about it. But in either case, it's plug in a number for perimeter, figure out what the area has to be. Great. So that is a function for area as a function of square's perimeter. Cool. Now how can we get its domain? Now, we talked about before, the domain is everything that we can plug in without breaking it. Now that's mostly true, but there's one little thing here. The domain also has to make sense, right? We can't break the world. So we wouldn't break this function, right? We could plug anything we want into this function, right? You plug in any real number in for p, and it would make sense. We'd get a number out of it, right? You could plug in 50, you could plug in 0, you could plug in -10. It makes sense. We'd get a number out of it. But the domain has to make sense. So it doesn't have to just make sense in our function. It has to make sense in how we thought about the function. How did we think about the function? It's a square, right? It's a real object. It's a thing. We could talk about its shape and how its dimensions are. Would it make sense for it to have a perimeter of negative? No, because it doesn't make sense for the sides to be negative. Would it make sense for the perimeter to be 0? No, because then it would just be a speck. It wouldn't be a square. There would be no area possible to be contained inside because we'd have no side lengths if we had a perimeter of 0. So it must be the case that our P perimeter is allowed to vary only from 0 up to infinity because it can't have a domain below 0 and it can't have a domain of 0 because while it doesn't break our function itself, it breaks the idea of what the function means. It is meaningless to talk about plugging in a perimeter that is negative or a perimeter is zero, because then it's not the perimeter of anything. We don't actually have a shape there. So we have to be having our domain make sense as well. So if we've just got a function, it can't break the function. But if we've got the function in the context of a word problem, it also has to make sense with everything else happening in the word problem. All right, hope that all made sense, because that just laid an important groundwork. You know, you're going to need to know this for the rest of your time in math, so it's really great that we got this covered here. Having a really strong understanding of what it means for something to be a function, it's going to help you out so many different places in math. It's going to help you with all sorts of things. Really great that we covered that here. All right, see you at Educator.com later. Bye.